Today, you may notice from the syllabus that in Chem 100, Exam 6, Chapter 15 is designated as a buffer day. That's for the lecture overflow if necessary. But since I finished the lecture on this topic already, and I want to get this review done as soon as possible, so you'll have plenty of time to work with it before the exam next Tuesday, we're going to do the review today. I'm pretty sure I can get finished with it today. So I picked out some problems that I want to use from the review document, and we're going to take them as indicated. So let's go to number 1. Okay. How many grams of calcium chloride, and the molar mass is given, are needed to prepare 5.17 liters of 0.5 molar calcium chloride solution? Now, this could be in any solvent, but for our purposes, you can assume that it's aqueous. So calcium chloride, right? What do we need to know? If we're going to calculate the molarity, we need to know the definition. Molarity is moles per unit volume, and volume has to be in liters. Okay. So do we have moles? No. Actually, we don't have even mass, because that's the question. We want to produce a solution that is 0.5 molar. And we want to know the mass. Well, we can't get the mass directly from this expression, but we can get the number of moles, and then the moles can be converted to mass. So our final volume is 5.17 liters. Okay, so we just solve for the number of moles, and the number of moles equals 0.5 divided by 0.5 molar times 5.17 liters, because molarity means moles per liter. That way the liters cancel. Okay, so half of 5.17 is the number of moles required. Is 2.585. And I'm going to keep an extra decimal, like I've said before. Since all of our operations are going to be multiply, divide, the significant figures can be calculated at the end, can be determined at the end. So in order to avoid rounding error, I'm going to keep an extra decimal. Now we can convert this to mass. We need grams per mole, molar mass, 110.0. And I get 284.35 grams. Now we can round it to significant figures. We started off with 3 here and 3 here, so we have to round off to 3 here. $284 grams. Now, why is the closest answer 287? Probably because I kept that value right there. And in the setup for this problem, whoever created the problem probably did a rounding here. So we've introduced a rounding error of 3 grams. Right? So that's about it's a little more than 1% error. You know, that can be significant. But as far as test taking technique goes, pick the best answer. And the best answer is B. Let's go to number 2. What mass of solute is contained in 64.9 milliliters of 2 molar sodium bromide solution? All right, so we're back to the same formula, but now we want to calculate the mass of the solute that's contained in this amount. Well, again, we have to solve for moles because we can't get mass out of that expression. But we can get the number of moles, right? So we have 2 molar solution. And what's the volume? Well, the volume is given in milliliters. That won't give you moles, that'll give you millimoles. So we want to move the decimal place 3 times to the left. Remember, 64.9 milliliters. The unit's getting bigger, so the number has to get smaller. And the ratio is 1,000 to 1. So we move it 3 places to the left to make that number smaller. And that's 0.0649 liters. There we go. That will give you moles. Okay. We go 649. And that's 0.1298 moles. Okay. What's the mass of the solute? Sodium bromide. Okay, in this case, you're not given the molar mass. You have to write the formula. Sodium bromide, right? +1, -1. Now we can determine the molar mass. Sodium is 23. And bromine is 7990. (102.9 grams per mole). Yeah. So now we convert this to grams. It's 102.9. And I get 13.3564 grams. The controlling significant figures here will be these two, 3 and 3. So we round this one to 3. 13.4 grams. Okay. Right. Number 3. You have 3 liters of 3.67 molar solution of sodium chloride. And you also have 2 liters of a 2 molar solution of silver nitrate. When you mix these two together, you make a new solution, of course. The question is, do you get a reaction? And then can you calculate the concentration of silver ions in solution after the reaction? Now, there's another problem, number 6, that's based upon the same conditions. Let's see. Yeah, okay. We'll do this one first. So what do you do first? Well, the reactants are given. So we can put the reactants up there and then deduce the products. Okay. What you get is a double replacement. The silver is available for chloride and the sodium is available for nitrate now that they're mixed together. So if we put silver chloride together, then we have leftover sodium nitrate. And then you look at your solubility chart and you find that sodium nitrate is still soluble. So it's still a bunch of ions in solution. Sodium chloride, though, is a solid. So let's see, is it balanced? One sodium, one chloride, one silver, one nitrate. It's already balanced. So now let's put what we know up here. We have 3 liters of 3.67 molar. And silver nitrate, we have 2 liters of 2 molar. Yeah, that's given. Question is, what's the concentration of silver ions left in solution? Where did the silver ions came from? The silver ions came from here, right? And we have given amounts of both reactants, which means that one of them is going to be limiting. If this is the limiting one, then you have no silver left over because it's tied up in that solid. But if this is the limiting one, you will have some silver ions left over, and then you have to calculate the concentration. Okay? So we want to find out what's the limiting reactant. How do we do that? Well, there are a couple of ways. One is just to say, all right, if this is all used up, how much silver chloride will it produce? And if this is all used up, how much silver chloride will it produce? And the least amount determines the limiting reactant. So we know that moles equals molarity times volume from our formula. So 3 times 3.67 is 1101. 0.01 moles of sodium chloride. Okay. And if we do this one, I'm going to shift it down here. This one would be 4 moles of silver nitrate. Okay. Now, we could calculate all the way over here, but we can also, let's say, what's the relationship between this reactant and that reactant? It's 1 to 1. So if all of this is used up, you need 11 moles of this one. You don't have it. If all of this one is used up, then you only need 4 of that one. This is excess. This is limiting. So what does that mean? That means all of the silver ions that were in solution here have been consumed, and you have no silver left over. That's why the answer is 0 molar. There's no silver ion left over to calculate the concentration. All right. Okay. So let's scroll down to 6 and use this same scenario to answer number 6. All right. Now the question is, for number 6, calculate the concentration of sodium ions in solution. Okay. Well, were the sodium ions consumed in the reaction? No. We've got sodium ions here. All of those sodium ions show up over there. So it doesn't matter what happens here. They're still in solution. How many moles do you have? Well, you have 11.01 moles of sodium chloride, and the ratio is 1 to 1. So you also have 11.01 moles of sodium ions. Okay? But what has changed? What has changed is the volume, because we added 2 liters here with 3 liters. Now it's that many moles, not per 3 liters, but per 5 liters. So we take 1101 and divide by 5, and we get a concentration, three significant figures, 2.20 molar. Moles per liter gives you 2.2. Well, and there we have a rounding error again. D. D is the closest answer to this one. Okay. Now we're going to go down to 47 because it's based upon the same conditions. And we'll come back after we finish this one. There's 47. There we go. Let's see. Now, do we have the same conditions? Hold on a second. I think I made a mistake. It's the same reaction, but I think the conditions changed. Yes, they did. Okay. So it's the same type of calculation, except in this case, we've got 3 liters of 3.48. So that did change. All right, so now we have, oops, it's not right. 3 times 8 is 24, 2 and 12, 14, 1 and 9 is 10. There we go. This is still excess. So now we have 10.44 moles of sodium ions per 5 liters. I think that will probably give us the expected answer. Yeah, 2.09. There we go. Okay, so now let's go down to 47 and see what conditions have changed and if that actually changes the outcome. 47, there we go. Okay. So now we're at 47 with the same reaction, but the conditions have changed, 3 liters and 3 molar. Okay. So that's 9 moles of sodium chloride. And we still have, and 1.48 now. Here we go. So this is going to change. That's 9. And this is, let's see, 16, 189, 2.96 moles. This is still limiting. This is still excess because it's 1-to-1. You only need 2.96 moles out of that much. So this is excess, that's limiting. Okay, now what's the question? Calculate the concentration and molarity of nitrate ions in solution. Well, this is a similar situation to number 6 because sodium ions and nitrate ions are both spectators. So all we have to do is find out, well, we have 2.96 moles of silver nitrate. That means we have 2.96 moles of nitrate ions. Do we have the same volume? Well, let's see, 3 liters and 2 liters, yes. So we have 5 liters divided into 2.96. And we have 0.592 molar, 3 significant figures. Let's see, what did I do wrong? Calculate the concentration and molarity. Oh, in solution C, I got to read my question. That's the ending concentration, but what's the concentration in solution C? The concentration in solution C, well, that is solution C. Let's see if I did that right. 1.48 molar, 1.84. Now that's dyslexia kicking in. 1.84. Okay, so now we have a different value here, we have a different value here. .368. Okay. And in solution C, which is this, right? This is A, this is B, this is C. Would be in 5 liters. 0.736 molars. There we go. Attention to detail. Looks like we got another one based on the same reaction. 52. Okay. So let's see. Let's move this one. And we'll take all of this out. And then we'll check on these values. 3 liters of 3.77. 7. And B solution is 2 and 2. So it's back to 2. So that gives us another, that gives us 4 moles of silver nitrate. And this one gives us 11.31 moles of sodium chloride. Okay, we've still got, that's limiting. This is excess. What's the question? What's the concentration of chloride ions in solution C over here? Well, if this is excess, then we're going to have some chloride ions left over. So what we have to do is say how many were consumed and how many were available, and subtract. Then we get what's left over. So what did we use up? Well, this is 4 moles of silver nitrate. It's going to lead to 4 moles of silver chloride. Right? So how much was used? Well, the ratio is 1 to 1. So 4 moles of chloride ions were used. How many did we start with? Well, 11.31 moles of silver chloride means 11.31 moles of chloride ions. This is start. And used is 4. All right? So what's the difference between those two? 7.31 moles chloride remains. And now we calculate the concentration based on the final volume, which is 3 plus 2 is 5. And that should be 1.46 molar chloride. You still have a significant amount of chloride left in that solution. And I believe that's it for that reaction. So now we can go back to where we left off. We picked this up at 3, so we'll start at the next one beyond 3. All right, so let's go back up. There's 3. And we're going to go down to 4. The molarity of chloride in 110 milliliters of solution containing 3.22 grams of calcium chloride is. All right, 3.22 grams of calcium chloride. That's what we're given. What's the question? What's the molarity of chloride ions in 110 milliliters of solution? So the volume is 110 milliliters. Right? That's the wrong units of measure. We need to change that to liters, which will be 0.110 liters. Now we need to find out how many moles of chloride there are. Right? We can find out how many moles of calcium chloride there are, correct? All we need is the molar mass. So we found that in a previous problem, didn't we? Let's see, where is it? 110 grams per mole. Okay. So we'll divide that into 3.22. And we get 2.97, oops, 2.927 times 10 to the minus 2 moles of calcium chloride. We're after the chloride ions. So in this solution, for every 1 mole of calcium chloride, there are 2 moles of chloride ions. So once that calcium chloride breaks apart in solution, it produces one of these, or it produces 2.927 times 10 to the minus 2 moles of calcium, but it produces 2 times that, or 5.85 times 10 to the minus 2 moles of chloride ions. So now we can plug that value in here, times 10 to the minus 2 moles of chloride. Divide that by 0.110, and we get 0.532 molar in chloride. Well, we're kind of off a little bit, aren't we? Let's see if I made a mistake. 322, 110 milliliters, 110 grams per mole. So did I calculate that one correctly? Let's see. Yep, that one's correct. And that one's correct. So this one divided by 0.11 gives you 532. Okay, so pick the best answer. The closest one to that one is C. All right, moving on. We're up to number 5. What volume of 12 molar nitric acid is required to prepare 6.71 liters of 0.1 molar nitric acid? All right. So let's do this. What volume? That's the question. Out of 12 molar. So let's see. What type of problem is this? We're given 2 concentrations, 12 molar and 0.1 molar, and only 1 volume. That looks like a dilution problem. So we want to know what volume of this concentrated solution at 12 molar nitric acid is required to make how much volume? 6.71 liters of diluted. At what concentration? 0.10. Oops, 0.110. No, 0.100. There we go. So now we can go to our dilution formula. Molarity of the concentrated times volume of the concentrated equals molarity of the diluted times the volume. And we can solve for the unknown. This is unknown. Divided by that. The advantage to doing it this way is you've already done your thinking. You've got your data in its proper place. You've thought through the problem. Now you have to do is plug in the numbers and crunch. So the molarity of the diluted is 0.100. I'm going to leave out the units for convenience. But you should be able to analyze this dimensionally. And concentrated is 12. Okay. And I get 5.59 times 10 to the minus 2 liters. The answer is in liters, correct? But it's in standard notation. So we move this to the left 2 places. 0.0559 liters. That's A. Okay, skip 6. We've already done that one. And we're going to number 9. Okay. You have 3 ammonium sulfate solutions on a lab table in front of you. All of the solutions came from 500 milliliter volumetric flask containing 3 molar ammonium sulfate. So there are your 3 solutions. But the problem asks a question about solution 2. That's the only one we need to know. How many moles of ions does solution 2 contain? So we focus our attention on solution 2, 68.7 milliliters of 3 molar solution. So we want moles of ions. If we've got a 3 molar solution and we're looking for moles, that's equal molarity times volume. Okay. So since the answer is in moles, we want to convert milliliters to liters. 68.7 milliliters. This is going to get bigger, so that one has to get smaller. 0.0687 liters. 1, 2, 3. Okay. So what does this tell us? This tells us 3 times 0.687. This is 0.2061 moles of what? Of the compound, ammonium sulfate. So what's ammonium sulfate? There's your ammonium. There's your sulfate. This is a +1 charge, and this is a 2- charge. So that means you need, that's your formula. But in solution, how many ions does it produce? It produces 3 ions for every mole, for every 1 of ammonium sulfate. So this is how many moles of that compound. 3 ions are produced, so you want to multiply that by 3. And we get 0.6183 ions. Moles of ions, excuse me. Moles of ions in solution. And the best answer to that one is E. Rounded off to 3, is that right? Yeah, it should be rounded off to 3. There we go. Okay. Number 10. That's starting to get a little weak. A mixture of sand and water is, well, what do you get with a mixture of sand and water? Is it heterogeneous or homogeneous? Well, obviously it's heterogeneous. Okay. So if it's heterogeneous, it can't be a solution, and the mixture can't be a solute or solvent. It doesn't even have both of them in there because we don't have a solution. We don't have a homogeneous mixture. So the answer is none of these. That mixture does not qualify as a solution or any of its components. So number 10 is E, right? None of these. If we had said something like a mixture of sodium chloride and water, that would be an aqueous solution. It would also be a solution, right? So one of the answers would have to be two of the above. Just as a hypothetical. Okay, number 11, a chemist needs 255 milliliters of 3.1 molar hydrochloric acid. What volume of 12 molar hydrochloric acid must be dissolved in water to form this solution? All right, this is another dilution problem. So chemist needs 225 milliliters. That's the diluted volume. Okay. And the diluted concentration is 3.1 molar. Let's see. Diluted concentration is 3.1 molar hydrochloric acid. Okay, so how about the concentrated factors? We're making it from 12 molar. Okay. The question is, what volume of 12 molar? Okay. So there you go. All right. The answer is in milliliters. And remember, the dilution formula is a ratio. We can choose any volume we want, and the answer will come out correctly. It'll come out in the units that we start with. So if we're solving for concentrated, right, we're going to go concentrated, concentrated, dilute, dilute. Then we're going to solve for this factor. Okay. And notice that if we use milliliters here, that's going to be milliliters also. So we just put in the value of 3.1 molar, and the volume is 225 milliliters, and concentrated is 12. I get 58 milliliters. Close enough. There we go. It works because this is a ratio. If it were the original formula, calculating the molarity, volume would have to be in moles. But since we've got a ratio, we don't have to bother with that conversion. All right, let's see. Scroll. 13. You have 250 milliliters of 4 molar sugar solution. I assume that's table sugar. You add 376.3 milliliters of water to this solution. What's the concentration of the sugar solution after the water has been added? This, again, is a dilution problem. So we're starting off with a concentrated solution of 4 molar sugar. So the molarity of concentrated is 4, correct? Yes, 4 molar. Okay. The volume of the concentrated solution is what? 250 milliliters. Okay. What's the molarity of the final solution? That's unknown. And we're going to add 376.3 milliliters. So what's the volume of the diluted one? It's not 376.3 milliliters. It's the sum of what you had before plus what you added to it. So this volume is 250 plus 376. Okay. And that is 626.3 milliliters. Now we can solve the problem. For this value right here. Okay, what's the concentrated? 4. Volume of concentrated? 250. And the volume of the dilute? 626.3. And I get 1.60. Yeah. Molar. Okay. Now, what would have been the answer if we get it wrong? If instead we stuck with 250 here, 376.3. If we had put 376.3 in there, we would have gotten 2.66 molar. Okay. You might be tempted to circle E because it's closer to that one. But unfortunately, that would be wrong. Okay. Excuse me. Number 14. You have 2 hydrochloric acid solutions labeled A and B. Solution A has greater concentration than solution B. Which of the following statements are true? All right. We have 2 solutions. Solution A, solution B, both of hydrogen chloride in aqueous solution, hydrochloric acid. Okay. So what's their relationship? A has a greater concentration than B. So the molarity of A is, well, let's do it this way. Molarity of A is greater than the molarity of B. There you go. So what does that mean? Well, it also means that the moles of A per volume of A is greater than the moles of B per volume of B. Right? These are 2 separate solutions, and that's their relationship. Okay. We're looking for which of the following statements would be true? Could be more than one. Selection C says at least two of the above statements are true. So we've got to look at each one, A, B, C, and E, to determine if two or more are true or if it's just one. Okay, so what does A say? B, C, and E. Well, D would be two of the above. So two above. Actually, two of the others. So A says if you have equal volumes of both solutions, if these are equal, solution B must contain more moles than A. If the volumes are equal, the only way that this quotient can be bigger than that quotient is if the numerator is bigger. So A is false. B, adding more moles of hydrogen chloride to both solutions will make them less concentrated. Well, that's just ludicrous. If you increase the size of the numerator of both of them, it'll make both of them more concentrated. Now, we don't know their relationship. That's not important for this question. At this point, we don't know if that would make one of them more concentrated than the other. But it does say that adding more makes them less concentrated, and that's false. C, to obtain equal concentrations of both solutions, you must add a certain amount of water to solution B. If solution B is already less concentrated and you increase the volume, you're going to dilute it, right? You increase the denominator, you decrease the value of the quotient. So if you increase that, you're going to make this one even smaller. So you can't make equal concentrations here because you're going to make this one even smaller than it already is. So C is false. Okay. Well, it can't be D now because we only have one more choice. So by process of elimination, it's probably E, which says if you have equal moles of HCl in both solutions, solution B must have a greater volume. If these are equal, then the way to make this one smaller is to make that one bigger than that one. This is as much a math problem as it is a chemistry problem. E is true. All right, number 16. A 116.9 gram sample of nitric acid solution that is 70% HNO3 by mass contains how many moles of HNO3? All right. The concentration is 70% by mass. So what does that mean? 70% equals 70 grams of nitric HNO3 per 100 grams of solution. That's what that means. Parts per 100. 70 grams per 100 grams if it's mass, percent by mass. Okay. If we have a 116.9 gram sample, actually, I don't need to do that. 116.9 gram sample, then that will tell us how many grams of HNO3 are in that solution. And I get 81.83 grams of HNO3. All right? But that doesn't answer the question because the question is asking for moles of HNO3. So what we need is a molar mass, right? 1.01 for hydrogen. Nitrogen is 14. 14.1, I believe. Yeah, 14.01. And oxygen is 3 times 16. So 3 times 16 is 48. Then 14.01 and 1.01. So this is 63.02 grams per mole. Now we can take this and convert it to moles. 63.02 divided into 81.83. And I get, let's see, probably two significant figures. 1.3 mole. All right, they kept another one. They're saying 70%. Oh, yeah, three significant figures. My mistake. 1.30 of HNO3. Now, what kind of problem is this? It's essentially dimensional analysis. You have to know what dimensions you're working with, of course, before you can convert them. But it's basically a dimensional analysis problem. Unit conversions. 17. Okay. Determine the normality of a base if 93 milliliters of 1.8 molar HCl is required to neutralize 52 milliliters of it. Okay. Here we have a situation. I mentioned earlier, when we do titrations, if the base, say we're working with HCl, if the base is monohydroxyl, then we can use molarity. But we don't know what the base is. So we have to calculate normality, right? And normality is the concentration of hydroxyls per liter, or the concentration, hydrogen ions per liter, or hydroxyls per liter. If that's the case, then this formula works. The normality of the acid times the volume of the acid equals the normality of the base times the volume of the base. And with that formula, you don't have to know what the acid and the base are. You just have to have the values of normality, which is related to hydrogen ions, hydroxyl ions. So we're looking for the normality of the base. That's this one right here. So what we have is the normality of the acid times the volume of the acid divided by the volume of the base. Okay. So what's the normality of hydrogen chloride? Well, it only has one hydrogen per molecule. So the molarity and the normality are equal. 1.8 molars of 1.8 moles of HCl per what volume? 52 milliliters. All right. Well, let's see. Notice this is a ratio, right? The ratio means that we can use milliliters instead of liters. It works just fine. So if we do 52 milliliters, excuse me, and calculate that one, I get 3.46 times 10 to the minus 2. Now, if you're interested in units of measure, if you divide by milliliters instead of liters, you would get millimoles, millimolar, which translates also, since it's 1-to-1, translates to 3.46 times 10 to the minus 2 millinormal. Okay. Okay. Take a look at the answers. The answers are in normality. So we do really need normal here, molar and normal. So let's go back and do it. Looking ahead, 52 milliliters is 0.0520 liters. Now let's try it again. And let me try that. Let's see. 1, 2, 3. That's right. 1.8, enter. 0.052. Okay. So this gives us 34.6 molar. And that's also hydrogen ions, which is 34.6 normal. So this is going to be 34.6 normal. Yep. You sure I read that right? Let's back up. Let's back up and read the problem again. What's the normality of the base if 93 milliliters of 1.8 molar HCl? So I used the wrong volume. 1.8 normal. Normality times volume is moles. So we have that normal. What's the volume? Well, actually, this equals the normality of the acid. What's the volume of the acid? You know, I was going at this all wrong. I was making it more complicated than it needs to be. This is 93 milliliters. There we go. So what's the volume of the base? Neutralize 52 milliliters of the base. So the volume of the base equals 52. Okay, that simplifies everything. Now the normality of the acid is 1.8. The volume of the acid is 93. And the volume of the base is 52. And the value should come out in normality. And I get, let's see, 3.2 normal. There you go. It's a lot easier than I was making it to begin with. Number 18. Clean up some of this smudge. Yeah. Okay. Number 18. Magnesium metal reacts with hydrochloric acid to form magnesium chloride and hydrogen gas. All right, suppose we react an excess of magnesium metal with 19.8 milliliters of 3 molar solution hydrochloric acid and collect all the hydrogen in the balloon at 25 degrees and 1 atmosphere. What's the expected volume of the balloon? Okay, this is a complex problem, but the reaction is still the same regardless of what the questions are. Magnesium metal plus hydrochloric acid. Yields magnesium chloride which is completely soluble, plus hydrogen gas. Okay. Notice I wrote magnesium with 2 chlorines because magnesium is an alkaline earth. 2+ charge, halogen -1 charge, so we need 2 of them to balance. Okay, so we need to balance the equation. Well, we got 2 hydrogens over there. Let's put 2 over here. That gives us 2 chlorides, 1 making. 1 change in coefficient, and we're balanced. Now what are we given? Excess magnesium. Okay, that means the hydrochloric acid is limiting. So what is its value? 19.8 milliliters of 3 molar. Okay. More conditions. We collect the hydrogen gas in a balloon at 25 degrees C. Right? And 1 atmosphere pressure. Okay. And we want to know what's the volume. Okay. So let's work this backwards. If we want to know what the volume of this is, where are we headed? We're headed to gas laws. And in this case, this is a state function. We don't know the before or the after. We just know the conditions right now. So that means the ideal gas equation. Right? We want to know the volume. Right? So if we solve for volume, we get nRT over P. All right. What factors do we know? We know the temperature, which has to be converted to Kelvin. We know the constant, 0.08206 liter atmospheres per mole K. We know the pressure, 1 atmosphere. We don't know the moles. We have to find the moles. So that's the question. Find the moles. Then we can answer the question. So can we find the moles? Well, if this is limiting, right, and we multiply 3 times, well, that's milliliters. What would that be in liters? Like that. 1, 2, 3 liters. Now we can multiply 0.0198 times 3 is 5.94 times 10 to the minus 2 moles of HCl. Okay. How many moles of hydrogen gas are produced from just this much? We need to convert HCl, H2. This is 2, that's 1. So we need half of that. 2.97 times 10 to the minus 2 moles of hydrogen gas. Now we have all the factors we need to solve the problem, except now we need to add 273 to that. Okay, so volume is going to be the number of moles times 0.08206 liter atmospheres per mole K. Okay. And temperature, which would be 298 K divided by 1 atmosphere. Okay. So we've done all our thinking. Now all we have to do is crunch numbers. I've already got this one in my calculator, so I'm going to multiply it by 08206 and 298 divided by 1. So this in standard notation. So this would be 0.726 moles, K, atmosphere, liters. Okay. That was a complex problem. Okay, 22. Which of the following solutions contains the smallest number of ions? All right. It's time for Henry Ford. We need an assembly line here. So A through D gives us values and E says at least two of the above. So that means if E is true, then two of those above have to have exactly the same number of ions. Okay. So let's do A through D. Conditions, 246.8 milliliters of sodium sulfate. That. And actually it's 1 molar times 1 molar. Then 539.8. 539.8. Is this also 1 molar? Yes. But it's a different compound. Lithium nitrate. Lithium is +1 charge. Nitrate is a -1 charge. So that's it. And these are all aqueous solutions. I'm just leaving that out. 305.6 milliliters. 305.6 milliliters of 2 molar potassium hydroxide. Okay. And 189.6 milliliters of 2 molar iron 3 chloride. There we go. And this one is also 2 molar. Okay. So we want to find out the number of ions. The first thing that we can do is multiply volume times molarity and get, in this case, millimoles, because those are milliliters. So this will give us millimoles of the compound. Okay. Once we have millimoles of the compound, we want millimoles of ions. So we need another conversion. So for every 1 compound, how many ions do you have? Well, in this case, we have 3. 3 ions for every 1 compound. This one has 2. This one has 2. And this one has 4. Okay. So we can chain these together now that we've done all our thinking. 246.8 times 1, of course, then times 3. So that's going to be 740 millimoles of ions. The next one, 539.8 times 1 and then times 2. This is Yeah, this is 1080 rounded off millimoles of ions. The next one, 305.6 times 2 times 2 again is 1222 millimoles. And 189.6 times 2 times 4 is 1517. Okay. So the least number, and they're all different, so it can't be E. It must be A. A has the fewest number of millimoles of ions. And that's Henry Ford. What I did was, instead of writing this value in here, I went ahead, since it was already in my calculator, and just multiplied it by the next factor. Save some time. Okay, assume that vinegar is 0.852 molar solution of acetic acid. Okay, that's pretty close. It ranges. What volume of 0.2136 molar sodium hydroxide would be needed to completely neutralize 6.89 milliliters of vinegar? Okay. What we've got here is a titration, a neutralization reaction, where we have acetic acid in solution, sodium hydroxide in solution, and they're going to make this salt still in solution, completely soluble, plus water. Okay. So we have one of these, one of those, one of these, one of these. Hydrogen and hydroxyl makes one of those. That's a balanced equation. Since the equation is balanced with a monoprotic and a monohydroxyl base, monoprotic acid and a monohydroxyl base, molarity works just fine. So we can say the molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. If they were not equal, say if we had 2 or 3 hydroxyls here, we'd have to resort to normality to solve the equation. Or the other possibility is we would have to use stoichiometry of the equation, the balanced equation, and the coefficients to determine the outcome. But it's simpler to do it this way if you can. All right. So what are we solving for? What volume of base? That one right there. Okay, what's the molarity of the acid? 0.852. And the volume of the acid? Neutralized 6.89 milliliters of vinegar. Yep. 0.6, no, 6.89 milliliters. And the molarity of the base? 2136. There we go. Now our answer should come out in milliliters. Let's see, 3 significant figures. 27.5 milliliters of sodium hydroxide solution. Okay. 26. Okay. Reaction between silver nitrate and sodium chloride. Okay. So we looked at a reaction like this before. Silver nitrate and sodium chloride. Makes the precipitate, silver chloride, and sodium nitrate solution. Right? We're given 200 milliliters of 0.1 molar silver nitrate. Oops, wrong one. 200 milliliters of 0.1 silver nitrate. Okay. And 95 milliliters do better than that. 95 milliliters of 0.1 molar sodium chloride. Okay. The concentration of silver ions in solution after the reaction is complete. Okay. It's not giving us exact values. So the first thing we need to do is say, is the equation balanced? Can we check it? Yep. One of each, actually. Then we need to find out which one's limiting. Well, the concentrations are exactly the same, and the ratios are 1 to 1. So the smallest volume is going to be limiting. And this one is excess. Okay. Now that we know that, the concentration of silver ions in solution after the reaction, we will have extra silver ions left in solution after the reaction is complete. Let's look at each one. It says that silver concentration for the first one is 0.1 molar. Is that possible? For two reasons, no. Because you've got this concentration to begin with, you're using up some of them, so that decreases the numerator, moles of silver, and you're also adding two volumes together, so the denominator becomes bigger and your concentration is decreased. So that A is false with that first statement. How about B? Less than 0.1 molar. Yes, that's true. So this part, less than 0.1 molar silver, is true. Doesn't say how much less, it just says less. But not all of the silver ions are used to make the precipitate. That also is true because this is excess. So B is true. Now let's see, if we're in a hurry to finish this exam, we probably stop there because that's the correct answer. And there are no other wonky ones like 2 of the above, none of the above, that type of thing. but we can look at the others just for instructional purposes. Greater than 0.1 molar. No, can't be. You can't have a higher concentration than you started with if you're going to use some of them, plus you're going to dilute the solution with more volume. Can't be. Physically impossible. Less than 0.1 molar. Now that's true. Right? What else is in the statement? Even though silver ions do not react, false. They are diluted with the mixture. Now that last part of that statement is true, but the first part is false because silver does react. So that's what disqualifies D. And then E, 0 molar, all the silver ions are used up to make the precipitate. That is false. We know it's excess, so there will be some silver left over. And by the way, if this one's true, that one cannot be true. They can't both be true at the same time. That would be a logical inconsistency or a logical fallacy. All right, moving on. To number 29. Nitric acid solution containing 71% HNO3 by mass has a density of 1.42 grams per milliliter. How many moles of HNO3 are present in 2.36 liters of this solution? All right, let's put what we know up here. What's given? Given is 71% HNO3 by mass. So 71% by mass HNO3. This is concentration. Density, 1.42 grams per mil. Density, 1.42 grams per milliliter. And the question is, well, we have one more factor, 2.36 liter of solution. Volume, 2.36 liters solution. Now, what's the question? How many moles of HNO3? Okay. This is going to be a dimensional analysis problem. We know that this actually means 71.0 grams per 100 grams of solution. Okay. We also know the density, and we're getting to the volume, right? We can't use volume in here because that's not volume. It's not concentration by volume. It's concentration by mass. We need to convert it to concentration by volume. So that's where density comes in. Remember the density formula. Density equals mass per unit volume. So what we want is actually, we don't have to go there because this is grams of solution per milliliters of solution. Okay? So if we take this one and multiply it by this factor, we need to cancel grams of solution. This is the dimensional analysis part. So the grams of solution is on top already. 1.42 grams of solution per milliliter of solution. Okay? So that will give us the concentration in terms of grams per milliliter. 71 divided by 100 times 1.42. which is 1.0082 grams. Well, actually, grams of solution cancel. So it's grams of HNO3 per milliliter of solution. Okay. Now, how many milliliters is this? Well, 3 to the right? If the unit gets smaller, the number has to get bigger. So we go 3 to the right. 2, 3, 6, 0 milliliters. Now, if we multiply it by that, per milliliter, milliliters cancel, and that gives us grams of HNO3. 2, 3, 6, 0. So that's 2,379 times 10 to the third grams of HNO3. Now that we have grams of HNO3, we can convert it to moles. Grams per mole. So we need the molar mass of HNO3. We did that before. I can't remember it, so we'll just calculate it again. 14.01 for nitrogen and 48 for 3 oxygens. So that's 2, 0, 13, 63. Yep. 63.02. So we divide that value by 63.02. And that's, let's see, standard notation. Yeah, this would be in moles. Grams cancel. This will be 37.8 moles of HN. Answer is A. $38. Okay. For the minute, I thought I'd seen that one before and had already erased it, which is kind of dumb. But it looks to be different. So we'll start from scratch. $38. Two solutions of sodium chloride. Okay. So let's just say solution A and solution B. How about that? The first solution is 2 molar. And the second solution is 5 molar. Okay. You have much more of the 5 molar solution than you add the solutions together. So the volume of B is a lot bigger than the volume of A. That's what they're saying. You add the solutions together. Which of the following would be the concentration of the final solution? Well, let's see. If we have a lot more of this one than we do that one, and we combine you add the solutions together. Well, if they were equal, the concentration should be midway, right? Halfway in between, like 3.5. But we're closer to 5 because there's more of it. So we're closer to this side for the concentration. Which one matches? Well, it's not going to be close to 2. All right, let's see. A, B, C, D, and E. Let's just put the values up there. 7.235, 7.2, 3.5, 2948, 8, and the last one is 7. Let's eliminate the ones that cannot possibly be in. 7, you can't have a concentration higher than either one that you start with, because one is going to dilute the other one. Right? So 7 cannot be. It's impossible. Okay? I mentioned midway in between. If they were equal volumes, you'd end up with that solution. Well, if 7 can't be true, 7.2 can't be true either, because that's even higher. So it's between these two. So which one is closer to the truth? If this is the greater volume, the end concentration is going to be closer to B. That one. Right there. Okay? That's how we logically solved that problem. Okay, we already did that one. Now we're down to 50. What is the normality of 1 liter of sodium hydroxide solution that contains 18.2 grams sodium hydroxide? Okay, if we're going to put sodium hydroxide into solution, we know we're starting with 18.2 grams. We can calculate the number of moles, and we have 1 liter, right? So that would be molarity. So let's convert this one to moles, because if we don't convert it to moles, we're stuck. We can't go anywhere with it. So sodium is 23, oxygen 16, hydrogen's 1.01. So we have 1, 0, let's see, 7, 10, 3, 4, 40.01. So we divide 18.2 by 40.1. Oops. 40.01, and we get 0.4549 moles. Okay, this is moles of sodium hydroxide. The question is normality. So how many equivalents does this represent? There's only 1 hydroxyl per molecule. So this number of moles is also equal to the number of equivalents. Actually, I should write this. Hydroxides. There you go. Now you divide it by 1 liter. And you get 0. Let's see. 3 significant figures. 4, 5, 5. Normal. Okay. Takes care of that one. Next, 52. Let's see. Another sodium chloride and silver nitrate problem. Okay. 52. Sodium chloride plus silver nitrate yields silver chloride solid plus sodium nitrate in solution. Go. Now, what are we given? 3 liters of 3.77 molar sodium chloride. Okay. And that's solution A. Solution B is 2 liters of 2 molar silver nitrate. Okay. And you mix them together. We want the concentration of chloride ions in solution. So we're looking at excess chloride. Excess chloride. All right. Is that true? Well, let's work it like we did before. 3 times 377. So that's 1 and 21 is, let's see. All right, mess that up. 21, 2 and 21 is 23. 2 and 9 is 11. 11.31 moles of sodium chloride. Okay. And this one is 4 moles of silver nitrate. So for every 4 moles here, we need 4 moles there. This is excess, which means there will be chloride ions remaining afterwards. How many were actually used? Well, 4 molar, excuse me, that's not molar, it's moles. 4 moles of silver nitrate means that we're going to produce 4 moles of silver chloride because it's 1 to 1, which also means that's how much was used. All right. So this excess, and this is moles of sodium chloride, which also means 11.31 moles of chloride to start. And we used 4 moles. Okay. So that means 3, 1, and 7 moles of chloride remain. Okay. What's the concentration? Well, now we have to divide it by the total volume. We have 3 liters and 2 liters, which is 5. You know, I think we've worked a problem like this before already, haven't we? It may be duplicated. 7.31 divided by 5 is 1.46 molar chloride ions. Be that as it may, we solved the problem anyhow. $55. Hey. In the following acid-base neutralization, 1.61 gram of the solid acid. Let's see. That looks like phenol. Yeah, that's phenol, which is solid. Neutralized 11.61 milliliters of aqueous sodium hydroxide solution based upon this reaction. Calculate the molarity of the base solution. Okay. So let's see, what do we got? What are we going on? Sodium hydroxide aqueous. Plus the phenol, C6H5O. And this is, I put it in solution. Okay, that's all right. It is soluble. So what do we get? Well, the salt is going to be the sodium salt. This sodium C6H5O is going to be, and it's probably, yeah, it's soluble. plus water. Now, is that balanced? Yeah, that's balanced. Okay, now we're given 1.61 grams of this. 1.61 grams. Even though it's in solution, the amount of solution is irrelevant. 11.61 milliliters of aqueous sodium hydroxide. 11.61 milliliters. Okay. Since we have one proton and one hydroxyl, we can use this relationship. The molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. And the question is, what's the molarity of the base? Right here. All right. You know what? Let's find out how many moles that is. I think that would be valuable. Well, hold that for just a second. We may not need that. 1.61 grams. So we need the molar mass of that compound. Right? We have 6 hydrogens. Right? We have 6 carbons. And we have 1 oxygen. So let's find out what the molar mass of that compound is. Is 148.12. 148.12 grams per mole divided into 1.61 is 1.087 times 10 to the minus 2 moles of that compound. Okay. If this neutralizes that, we have to assume, otherwise we can't solve the problem. We have to assume that that is the total volume. And the total volume, this would have been solid to begin with, and it would dissolve as we add that one. So this is that many milliliters of that base. Well, actually, the total volume doesn't matter because we know that it's going to take that many moles of base to neutralize that acid. So this is 1.087 times 10 to the minus 2 moles per liter, which would be it's going to get bigger, right? This has to get smaller. 1, 2, 3. 01161 liters. I get 0.936 molar. Oh, did I calculate that wrong? I think I did. Let's do it again. How many moles of this? 6, 1, 8. That's right. 1.61 grams, 148.12. So that's correct. That many moles of this acid are going to be neutralized by that many moles of the base. That's true. And the volume, moles base per volume, is that correct? 11.6 milliliters. 11.6 milliliters would be 11.6 times 10 to the minus 3 liters. Moles per 936 molar. That's what I get. Let's see. I think I made a mistake. 1 second. I made a mistake here. 6 hydrogens, 6 carbons, 1 oxygen. Let me do that again. 6.06, 12.01, 6, and then 16. Yep, there's the mistake. This is 94.12. Let's try that again. 1.61, 94.12 is 1.710 times 10 to the minus 2. And that's 1.47 molar. There we go. That was the problem right there. Let's go to 59. What volume of a 0.176 molar sodium sulfide solution contains 1.01 grams of sodium ions? Okay, so let's start off with 1.01 grams of sodium ions is where we're headed. And what we're given is we want to know the volume of a molar solution. So the molarity of the solution is 0.176. Right? Molar sodium sulfide. Okay, what volume do we want? Well, if we're going to solve this for volume, molarity equals moles divided by volume. So we need volume equals moles divided by 0. Actually, if that's the concentration of the compound, what's the concentration of the ions, of the sodium ions? It's twice that value because you have 2. So this is going to be 0.176 times 2, 0.352 molar sodium ions. Right? So what we need is the moles. Now, as it turns out, sodium ion is essentially the same as sodium atom when you're calculating, when you're using molar mass. All right, because an electron is minuscule by comparison. So we can use the value for sodium, which is 23. Divide that into 1.01. And that's 4.391 times 10 to the minus 2. And then we substitute that here. That's moles of sodium ions. So 4.39 times 10 to the minus 2 millimoles. And divide that by this number. We get 0.125 liters. Our units are in liters, correct? Yeah. 0.125 liters. How many milliliters is that? Decimal to the right, 3 places. 125 milliliters is 0.125 liter. Uh, 62. Might run over just a little bit, but we're going to finish today. I think we're going to finish today. Yeah, I think we can finish. I'll run over just a little bit. 62, 15 milliliters of 0.3 molar sodium phosphate reacted with 20 milliliters of 0.2 molar lead-2 nitrate. What's the concentration of phosphate ions left in solution after the reaction is complete? We did one like this in class. I remember that. Sodium phosphate. This is your reaction. Plus lead-2 nitrate. All right, what precipitate is going to form? Well, sodium and nitrate is soluble. Lead-2 phosphate is insoluble. We have sodium nitrate. Okay, we need to balance the equation. And like I said before, these precipitation reactions are usually fairly well behaved. So you can use the budget method if you want, but we should be able to do it without. 3 leads here, 3 leads there. That's 6 nitrates. 6 nitrates, 6 sodiums, 2 here, 6 sodiums and 2 phosphate, 2 phosphate. Now we're balanced. Now what are we given? 15 milliliters of 0.3 molar. 15 milliliters, correct, of 0.3 molar. That solution. And then lead-2 nitrate is 20 milliliters of 0.2. All right. And the question is, what's the concentration of phosphate? Phosphate ions in solution. Okay, that's where we're headed. Well, first we have to find out which one's limiting. Do we have any phosphate left over? Because some of the phosphate is used up in that precipitate. So let's see. If we multiply 0.3 times 15, we get 4.50 millimole of sodium phosphate. Okay. Let's see if I did that right. 15.3. Yep. And if we multiply these together, we get 4. 4.00 millimole of lead-2 nitrate. Okay. Well, let's see. The ratio here is 3:2, so it's not as simple to compare these. Let's go ahead and calculate lead phosphate. So this is going to be converted like this to lead-2 phosphate. And the ratio is 1 of these for 2 of those. Okay. So that's going to be half of 4.5. 2.25. So this is 2.25 millimoles of lead 2 phosphate. That's what this would produce if all of it were used up. If all of this one were used up, lead 2 nitrate, and again, we want to produce lead 2 phosphate. The ratio here is 1 there and 3 there. So 4 enter and 3 divide is 1.33 millimoles of lead 2 phosphate. Okay, this one is limiting. So we will have some phosphate left over. Okay. Now, how much of the phosphate did we use up? Well, if it's 1.33 moles of lead 2 phosphate, and there are 2 phosphates for every 1 molecule, we used up 2 times that. Right? 2 times that. 2.66 millimoles of phosphate were used. How many did we start with? Well, we started with 4.50 millimoles of sodium phosphate, and since it's 1 for each, then it's 4.50 millimoles of phosphate. That's what we started with. And we used up 2.66. Right? So 2 times that and 2.66 and 4.5. So we're left with 1.84 millimoles of phosphate ions remain. Okay. And they want us to calculate the concentration of phosphate. Well, what's the final volume? Well, it's 15 plus 20, which is 35 milliliters. All right. Millimoles divided by milliliters equals molarity. Right. Normally we think of moles per liter, correct? Well, think of this as 2 separates, milli times moles, milli times liters. If we cancel the millis, we get moles per liter. So millimoles divided by 35 milliliters will give us molarity. And that's, let's see, standard notation. So let's see, 2 places over 0.0526 molar phosphate. Closest one there is A. That works. Okay. Let's go to 64. This is a fairly simple question. When a solvent has dissolved all the solute it can at a particular temperature, it is said to be saturated. That's definition. Saturated. Okay. 65. I think I need a new marker. If you mix 20 milliliters of molar sugar solution with 30 milliliters of 5.57 molar sugar solution, you will end up with a solution of a certain concentration. All right. So we have 20 milliliters of 3 molar, 20 milliliters of 0.3 molar. And we're going to mix it together with 30 milliliters of 5.57 molar. Okay. If we want to calculate the final solution concentration, what do we need? Well, if we're going to calculate the molarity, we need the number of moles per unit volume. Right? And since we've got milliliters, why don't we just stick with millimoles? Right? 3 times 20 is what? 60 millimoles. All right. How about this one? That's a little beyond me. Let's try it. I better do 30 times 5.57. So that's 16.7. 16.7 millimoles. That's the amount of sugar that we're putting in this. Well, that doesn't seem right. 167. There we go. 167.1 actually. Okay. So now the number of moles of sugar would be the sum of those two. And that's 227.1 moles, millimoles, excuse me, millimoles. 227.1 millimoles, and we need milliliters. So the final volume is 20 plus 30, which is 50 milliliters. And that should be 4.54 molar. Okay, there you go. Let's see, what do we got? Skip a few. 74. Fifteen milliliters of 0.3 molar sodium phosphate reacts with 20 milliliters of 0.3 mil lead to nitrate. What's the concentration of nitrate ions left in solution after the reaction is complete? All right, we put this reaction on the board already. What do we know from this reaction? We know that the spectators are nitrate ions and sodium ions. Okay, that means that the number of moles of those two ions will not change, but the volume did change. So we need to find out, if we're going to answer that question, what's the concentration of nitrate? We need to find out what's the number of moles of nitrate that we start with. So the compound is lead 2 nitrate, right? Lead 2 nitrate. There's your compound. And we're given 20 milliliters of that at 0.3 molar. We multiply those together, we get, let's see, 6 millimoles of lead 2 nitrate. Is that right? Yeah, that's right. How many millimoles of nitrate? Well, it's twice as many. 12 millimoles. So if we want to calculate the concentration, the molarity of nitrate ions, we need the moles, or in this case, the millimoles. If we're going to use millimoles, we have to have a volume of milliliters. So what's the total milliliters? 15 plus 20. Okay. 35 milliliters. Millimoles divided by milliliters is molarity. And that's 0.343 molar. A is your best answer. And we're done. Those are all the ones I had picked out. And if you can work that type of problem, each of those types of problems, you'll be just fine on the exam. And the only way you can get comfortable with working these problems is to work a lot of them. That's why that review document I give you and the sample tests that you can work in Brightspace gives you a lot of the same types of problems so that you can get a feel for that type. When you see that type of problem, you have an intuition about where to start, where to end. So I'm not giving you this many problems just to punish you. I'm giving you this many problems so that you'll get comfortable working them. Remember, your best friends in chemistry are curiosity and boredom. At least in this course they are. Okay, stop the share and we're done for today.